Hey guys, so in econometrics, we are interested in three key properties of estimators. The first one is unbiasedness. The second one is efficiency, while the third one is consistency. So the first two of these, that is unbiasedness and efficiency, relate to finite sample analysis. So what we mean by finite sample analysis is simply that the sample that we have taken has a finite number of observations. So on the other hand, consistency is a property which relates to analysis where the sample size tends to infinity. So in this video and the next few videos, we're going to be dealing with the first two properties. That is, we are going to be analyzing our estimator for unbiasedness and efficiency only. And later, we're going to be analyzing our estimator for consistency. So these two relate to finite sample analysis. Now, in one of our earlier videos, we have already gone through the proof that our estimator of the sample mean is an unbiased estimator. So this was our estimator, X bar, and we had proven that this estimator is an unbiased estimator. So the expected value of X bar is equal to mu X. So I'm not going to repeat that in this video, but in this video, what we're going to do is we are going to analyze another estimator, which is a generalized estimator of the population mean. So Z is equal to lambda 1 times x1 plus lambda 2 times x2. So this is the generalized estimator that we're going to analyze. And we're going to analyze this first for unbiasedness and then for variance. Okay, so to create space, let me just quickly erase this. Right, so this over here is our generalized estimator. And the reason we're analyzing this for efficiency and unbiasedness is to demonstrate the idea that the sample mean is not the only unbiased estimator of the population mean. So this generalized estimator that we have is basically defined as the weighted sum of two observations, x1 and x2, and lambda 1 and lambda 2 over here are the weights. Okay, so let me just write that. So lambda 1 and lambda 2 are the weights, and our generalized estimator is the weighted sum of two observations, x1 and x2. Now, first of all, to analyze, let me just erase this as well. So first of all, to analyze our estimator for unbiasedness, we will proceed as always. That is, we're going to take expectations on both sides. So our goal at the moment is to determine the condition that must be satisfied by these weights for Z to be an unbiased estimator. So we're trying to determine the condition that must be satisfied by lambda 1 and lambda 2 in order for Z to be an unbiased estimator. Okay, that's what we're trying to do. Right, so first of all, let's analyze this for unbiasedness. So let me just note that right here. Okay, cool. So as always, we're going to begin by taking expectations. So the expected value of Z is equal to the expected value of lambda 1 x1 plus lambda 2 x2. Okay. Now, by this stage, you should be pretty familiar with the expected value rules. So first of all, we're just going to use the expected value rule number 1. So using EV rule 1, we can decompose this into two separate components. So this becomes expected value of lambda 1 times x1 plus the expected value of lambda 2 times x2, and this becomes, now using expected value rule number 2, we can take out lambda 1 and lambda 2 so as a common factor. So lambda 1 times expected value of x1 plus lambda 2 times the expected value of x2. Okay, now if you have gone through my previous lectures where we discussed the idea that as a beforehand concept, so we discussed the double structure of a random variable, and we remember from those videos, we can recall that as a beforehand concept, the expected value of x1 is equal to the expected value of x2, which is equal to mu x. So as a beforehand concept at the planning stage, we know that the expected value of x1 and the expected value of x2 is simply equal to mu x. Okay, and the reason is that at the planning stage, the expected value of x in each observation, as I have already explained in those videos, as a beforehand concept, before we generate the sample, is simply going to equal mu x. Okay, so therefore we can replace this with mu x, and what we get is lambda 1 times mu x plus lambda 2 times mu x. Okay, now mu x is common between these, so what we get is mu x times lambda 1 plus lambda 2. Even if we don't do that, we can clearly see that the condition that needs to be satisfied by these weights lambda 1 and lambda 2 is that so we need to write this down. As always, we have to explain our conclusions. So we can conclude that Z is an unbiased estimator if and only if the sum of these weights, that is, if lambda 1 plus lambda 2 is equal to 1. So we can see that clearly, right? So if lambda 1 plus lambda 2 are going to add up to 1, then all we're left with is going to be mu x. Therefore, we conclude that Z1 is an unbiased estimator. Let me just rewrite this because my handwriting can sometimes be illegible. Okay, cool. So Z is an unbiased estimator if and only if the sum of the two weights, that is lambda 1 plus lambda 2, is equal to 1. So if sum of weights equals 1. Okay, so we're done with the first property, that is unbiasedness. Now we are going to move on to the second property, that is variance. Efficiency. Okay, so I just noticed that this lecture is already almost 9 minutes long. So in the next recording, we're going to analyze the efficiency of our generalized estimator.